Welcome to video 10 in our first Principles of Astrophotography series. In this video we discuss stretching, a technique for bringing out faint details in an image without overexposing its bright regions.
Are you seeing some faint details?
I'm seeing some bright regions here.
Don't look at my bright regions. Stretching is an essential step in post-processing images. It's also crucial to understanding star sizes in images, as we discuss in video 11.2
Coming
in the
up.
future. Yeah.
This video is based on chapter 10 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 119, stretching. Stretching is the process of mapping measured light intensity levels into pixel brightness levels in order to bring out faint details in an image without overexposing its brighter regions. It's a good description, but
It's complicated.
A little hard to understand.
When you're first, you know, stretching was very mysterious to us when we got into this business. So this is an image that we're very proud of, the Andromeda Galaxy. It's 22-hour integration taken in late 2024 from our Bortle 2 site with our CAT 91 and ASI 6200, as well as the Antlia V series LRGB filters, luminance, red, green, blue, and then the Antlia H alpha 3 nanometer. No, it's 2.5 nanometers, isn't it? Or ours 3 nanometer or 2.5?
no, I think that's 2.5.
I think they're 2.5. So that's a lie. So this is, of all those frames we took of over 20 plus hours, these are 77 luminance frames, 3 minutes each for each exposure, with no stretch at all applied to the data. So what you see compared with the entire galaxy that's been stretched and carefully processed, in an unstretched image, this is what you see. Mostly completely black with a few little super bright spots that you can actually, you're able to see. You can see the core of the galaxy. You can see the neighboring satellite galaxies, the core of them. Well, maybe not even the neighboring. Yeah, you can see this galaxy right here, but I don't think you even see this one. Yeah, it doesn't even show. And then a few of the bright stars show up in the image. But the bottom line is that if we published an image like this on Astrobin,
We would not win image of the day.
we would. I was thinking we get ridden out of town, but
maybe
we
that.
definitely won't get image of the day. So that's the deal. Why is this image so black? And that was one of the things that we wondered about when we first got into this. I don't know if you wondered about it, but I did.
Oh, yeah.
Okay, here's why it is so black. This is a histogram. This represents the measured ADU value.
Or brightness value.
Mm-hmm. Well, it's I call it the intensity
yes.
value.
Yeah, good call.
So it's the intensity of the light that reached the pixel. This is the maximum ADU value, which for our sensor is 65,535.
Mm-hmm.
Like we talked about in a previous video. So if a pixel has an intensity of 65,535, then little x would be 65,535. Big X is always 65,535, and 65,535 divided by 65,535
I win.
gives our old friend
1.
1. And since we're putting this in percentage, 1 would be 100%.
Easy peasy. Yeah.
So that would mean that that a fully saturated pixel will be up here. A little x of 0 means that ADU value is 0. So everything is between those two extremes. Now what does this mean? NX. NX is the number of pixels with intensity X. So for example, if all of the pixels on the sensor were completely saturated, then what the histogram would look like is 0, 0, 0, 0, 0, and then boom.
Yeah.
Everything would be completely saturated. You'd see just a bazillion pixels up here on the fully saturated. If none of them were illuminated at all, if there was no light, like a dark frame or whatever, dark calibration frame, then it would be down here. So the point of the matter is here, for this Andromeda Galaxy, which is a bright object, I mean, we're not talking about one of those spaghetti nebula that are really, really faint
Yeah,
or whatever.
no.
We're talking about an extremely bright object.
Yeah.
Almost all the pixels are very, very,
What's the magnitude of Andromeda?
it's like 3 or 4 or something like that. I mean, it's
gigantic, yeah.
It's you can see it with your naked eye on a clear dark night. And so for goodness sakes, for that bright of an object to have so few bright pixels over the scale, it just tells you how dim, what this does is it just tells you how dim objects are in the sky.
To the
And
camera. How dim to the camera.
Uh-huh.
Yeah.
Not dim intellectually.
No.
Yeah, no. Yeah. So, so now, what does this actually mean? It means that 99% or more of the pixels are down here at very, very small values of x, near 0. This scale up here is the brightness. So if you're not going to apply a stretch to the image, then all these pixels get mapped to this brightness on the image,
Yeah.
which is indistinguishable from black. And then the few little pixels that come up here, there are some that are probably saturated. I don't know, probably the
In the very center, yeah. Yeah, I
the
bet
center
there's
was
some
probably saturated.
Yeah.
But there's so few of them that you can't even see that white curve come up here.
Yeah.
So those are the ones that are white up here. That's why a linear stretch just is no bueno in astrophotography, because almost all those pixels are going to be extremely faint. The intensity of the light coming in, the photons are just coming. We did a calculation in one of the later chapters, one of our images we took, we figured that we got one photon every 15 seconds. So that's in a later chapter. A really, really fun calculation to think about. Okay, here comes one photon. Okay, here's
Roll
another
on.
one. Yeah. So that's a histogram. It measures the number, and we're talking about the entire sensor here. So we've got a sensor, sensor array, and here's one pixel. We figured out, okay, what's the value of x? And if the x over big X is 40, then we add 1 to there. And then we're looking at all the 61 megapixels in the whole camera when we do that. Okay, so this is that same data with a midtone transfer function stretch. And in the book, we give this specific mathematical form for the midtone transfer function stretch, sometimes called the or just abbreviated the MTF stretch. It's probably the most popular stretch that's used, right? As opposed to logarithmic and inverse arc sine and et cetera, et cetera. It allows you to set a black point and a white point and the midtone parameter FM. Those three parameters, all three between 0 and 1, determine how much you stretch the image. And I'm going to show you some pictures of what that stretch actually looks like, I think, right now. But I think you can see that this stretch has brought out the faint regions without overexposing the bright regions.
Yes.
So again, the mathematics is in the book if anybody's interested. The linear stretch is this black curve right here, curve A. That basically says that this is the intensity. So it's the intensity of the light received by the sensor. I before E.
Except after C.
By the sensor. And this is the brightness of the pixel in the image. That's an I. What stretching is all about is trying to map the intensity of light received by a pixel into the brightness of the actual final image. That's what it's all about. So this linear stretch, A, is just a one-to-one mapping straight across the board. Most of our pixels in the image were way down here in the 1 or 2% range.
Yeah.
And therefore, most of the pixels in the image were just plain old black, very boring. B is a piecewise linear stretch, this orange curve, where you're flat for a while, and then you have a straight line, and then you're flat again after that. And I'll show you some piecewise linear stretches. Then these are nonlinear stretches. A logarithmic stretch, an inverse hyperbolic sine stretch, and a midtone transfer function stretch that we talked about a minute before. They all look pretty similar. A couple of interesting things to note is that logarithmic stretch, actually the slope right here is infinite. It goes straight up right there. So it's an extremely strong stretch for bringing out those faint details. But then up here, the intermediate details that aren't quite as strong, it's a little weaker there. So, and again, the midtone transfer function, its slope is not infinite initially here. It has a finite slope, rise over run. And I honestly think the differences between the C, D, and E are not that great, although you're the processor. And you can get good results with any of these. I mean, ASTAP uses a inverse hyperbolic sine stretch. That's all that's available. I think most people in PixInsight use MTF. Is that true?
Yeah, I think so.
Most people. Yeah, but I think you can get good results with any of these.
Principle 120, stretch parameters. Intensities at and below the black point map to black. Intensities at and above the white point map to white for grayscale channels. And to full color for color channels. The midtone intensity maps to midtone gray for grayscale channels and to midtone color for color channels.
This is the black point, and this is the white point. These aren't stretches we applied to anything. This is just a graph I put together to show what everything means.
Why don't we start because we're starting at the point of moved in on piecewise linear.
Right, so we're just choosing the same black point and white point for the piecewise linear as we are for those three nonlinear stretches. It's just to show what that doesn't mean.
So I can still start my stretch at 0 if I want to.
Yeah, you certainly can.
Yeah.
And normally, I think you told me, most people set their white point at 1 anyway, right?
No, I don't know.
I think you told me that usually people set their white point, the default on PixInsight for the white point is 1.
Makes sense.
I don't know.
Yeah.
But the point of the matter here is that at and below the black point, the pixels are completely black. That maps them to this black region right here. At and above the white point, the pixels are completely white. And then the real difference between all these different stretches is how you get from the white point to the black point. So that's the black point, that's the white point, and then the midtone intensity. This will become really important when we talk about star sizes in an image. The midtone intensity maps to midtone gray. These are midtone intensities for the 5 different stretches. So what I mean by that, let's look, for example, at the midtone transfer function stretch, which is green. That one here, E. So starting at the black point here, we're moving up here, and when I reach halfway up, when I reach 0.5 of brightness with midtone gray, that's right in the middle between black and white. When I reach that point is defined as the midpoint intensity. The midtone, not midpoint, but midtone. Why? Because this is a midtone gray. And so what the midtone transfer function stretch does is it allows you to actually adjust that midtone intensity. Whereas a logarithmic and inverse hyperbolic sine, you adjust different parameters, which does adjust the midtone intensity, but you don't adjust it directly with the midtone transfer function.
Yeah.
Okay, so as you can see here, for example, for the logarithmic, which is the blue curve C, its midtone intensity is lower. The one that maps to midtone gray is lower, and we've stretched it a little bit strongly.
Visibility threshold, principle 121. Pixel brightnesses that are less than or equal to 1/10 of the maximum brightness are visually indistinguishable from black.
So let's take a look. These are pixel brightnesses. This is a pixel brightness, again. And ones that are below, between 0.1, which is 1/10, and 0, are visually indistinguishable from black. So that's just something that I looked at and I thought, I can't tell any difference between that and that. Just my eyes. Can you?
No.
And I'm beginning to start to see some difference. I'm saying, okay, yeah, that's a gray. By the time I get to there, it's kind of like the resolution image. When can you tell that it's 2 lights versus 1? Well, there's a whole spectrum in there. But basically, if you're down below 0.1 in the brightness, then it's basically going to be black. And that is why that image looks the way it does.
Yeah.
These are ones that we actually applied to the Andromeda Galaxy, to that image. And number 4 is the one we've already looked at. That's the stretch that we applied to get that beautiful image of the luminance frames. But first, looking at linear unstretched data, notice here that I'm not taking x all the way up to 1. I'm only going up to 1/10, because I just want to focus in on most of these stretches. So if I were to plot this all the way out to 1, then
It would be 10 times longer.
it'd be 10 times longer, or if we squished it up this way, we wouldn't be able to tell these curves from each other because they'd be squished against each other.
Right.
So that's why we're only going up to 1. The weak piecewise linear, that's this stretch here. So we chose a white point for this weak piecewise linear, a white point of about 0.02, 0.03 it looks like. So here's linear unstretched. Here's a piecewise linear. You're still not getting the detail that we saw out here. Strong piecewise linear. So that's this one here. So now instead of the white point being about 0.03, now the white point is down less than 0.02. So we've really stretched it pretty much as far as we can go with a piecewise linear. So what do you see in that stretch?
I see more nebulosity outside.
You see more nebulosity
whatever we
outside.
call it.
But
Yeah.
what do you see inside?
Nothing.
you see completely blown out interior.
Yeah.
So the whole goal of stretching is to bring out the faint details without blowing out the interior, the bright regions. So that's a fail. And then finally, the midtone transfer function, which we already showed you before. I mean, some might argue that that's a tiny bit blown out in the middle, but
Yeah.
it's a bright galactic core.
Yeah.
And we can still see these details and hear these dark lanes, whereas in the strong piecewise linear, I mean, there were dark lanes right here we can't even see in that.
Yeah.
Stretching is an art, and that's why Ren does all of our stretching. And, I only stretch before I run, and
nice.
he stretches our images. And I did stretch these with, I think I used ASTAP. I'm a Pix Insight dropout. Well, I never actually took the course, so I never
You
dropped it
refused
out.
to.
I refused to.
Yeah.
Yeah, one day Ren sat me down. These were our serial days. You remember that?
Yeah.
We started off in serial, and Ren sat me down and he said, "Okay, Dad, I'm going to teach you serial. So download the." It was right over on my couch. Download the software. Here's what you need to do. And I went, too much information. I'm not doing it. We have a division of responsibility here, and you're overstepping your bounds on our division of responsibility.
Stretch is 122. The logarithmic stretch, inverse hyperbolic sine stretch, midtone transfer function stretch, and generalized hyperbolic stretch bring out faint details of an image without overexposing brighter regions.
Bottom line.
That's what we want.
And yet again, it's our image of the Andromeda Galaxy.
Love that thing.
So, tell our admiring audience how many hours you spent on trying to process that image. Or maybe not admiring audience. Maybe it's our haters. Tell the haters out there.
Yeah. Or the people who just feel bad for us.
So we're talking about 10 hours. We're talking 30. We're talking
maybe
5.
Maybe 20. I honestly don't remember. Up to the last few images, I kind of averaged maybe 10 or 15, maybe 20 hours per each. And this one was hard because we had some headlights that we had issues from the telescope on, and yeah, we wanted to get it just right. And I just love all the inside stuff, all the detail inside that.
It's, and then you can, if you look this one up on our Astrobin page, it's under the name Reynolds Edwards. You can zoom into it, just a huge 3 or 4 times zoom, and still see more details. It's really beautiful. Thank you so much for watching.
And we will see you next time.